My name is Kartik Paramasivam. I manage the streams infrastructure at LinkedIn, or the near real-time data processing infrastructure. Me and my teams focus on our PubSub messaging system, which is based on Apache Kafka, stream processing system based on Samza. We also run it as a service at LinkedIn. Our nearline data pipelines, change capture, streaming SQL, things like that. And today we're going to explore what would be the ideal world for stream processing. A world where someone tries to build a new app, they don't have to worry about how hard near real-time processing is, and they feel confident that they can get their job done in a meaningful amount of time. All right. I do have a lot of material, so I'm going to go a little fast. Apologies in advance for that. We're going to talk about the current state of the union, and then we'll get into the meat of the talk. Most of you already know where near real-time processing is being used today. It's used everywhere, practically every vertical you can think of. At LinkedIn, we use it obviously for social computing, but also for kind of security, application monitoring, bot detection, all kinds of things. A good reflection of how this has progressed over the last few years. This is kind of a graph of the streaming data at LinkedIn. And every time we added a few more trillion messages, we thought it's going to slow down, but turns out it just keeps on going. Yeah, it's kind of staggering where it is right now, but we expect it to continue to grow. We ingest like more than a petabyte a day. And all of this is also attributed to the growth in stream processing. So there's just a growth in number of streaming applications at LinkedIn. As you can see, that it's kind of very clear hockey stick growth. As we are making our platform better and better, we are seeing a lot more of this coming up. And as we do more stream processing, that also increases to the amount of data that we inject into the system. All right. So another reflection of the growth is the number of technologies out there for stream processing. It's very crowded. Some are good at one aspect, others are good at another aspect. The good thing out of all of this is there's a lot of competition, and hopefully over the next few years, most of them will mature, and you'll be able to get your job done easily. At LinkedIn, we use Apache Samza, which is a top-level Apache project since 2014. We use it primarily for its stability, reliability, and scalability, and we'll talk about some of the lessons that we've gotten from there. It's also used by a bunch of other companies. Before we go any deeper, I wanted to kind of put an architectural context around this stream processing discussion. And this is a fairly canonical architecture, practically in every space, but it's similar to what we do at LinkedIn. In essence, there are all of these clients or devices that are talking to typically a services layer. And the services layer usually either updates a set of databases, or it's sending some events into an ingestion system like Kafka. Turns out that both of these things are very relevant for near real-time processing. All the updates that are happening to your databases, at LinkedIn, we have a homegrown database called Espresso. We also use Oracle, MySQL, you name it. These are kind of, these changes are basically captured and made available via Kafka for downstream processing. Some of the other databases like Cosmos DB or DynamoDB already have a streams offering, so you don't need like another change capture system. You can directly process events out of them. And yeah, and at the end, all of this gets processed by a stream processing system. All right, so with that, let's get into what would be the ideal world for stream processing. So in the ideal world, as I see it, if someone wants to build a new application, they should be able to kind of use near real-time processing for doing any kind of complexity, have an application of any complexity, run it at any scale, and that's actually pretty tricky, by the way, and we'll talk about why it is. process data from any source, and because there are a lot of sources out there, and use their language of choice. And language is a big deal because depending on the language, it could be very hard for certain people, and so the right language is very important. And of course, they want to run it anywhere, right? Because there are a lot of environments out there, and you want to run it in the environment that makes sense for you. And none of this is going to work if you don't have really awesome tools that make it easy to use. So let's talk about the first aspect, which is complexity. What do I mean by complexity? Well, so to start very simple, in terms of the types of near real-time processing, you can put in 2 buckets: stateless, stateful. Stateless is basically message in, message out, and you can do a bunch of filtering, transformations, things like that. Stateful is when you get a bunch of messages in, but you don't produce these messages out immediately. You wait for a trigger, so you accumulate some state for a period of time, after which you generate your results. So let's take some examples and talk about talk about the complexities in each. This we already talked about in a filtering, simple stateless application. It's very easy to code up in any stream processor out there. There's some code from SAMZA, some code snippet. Let's make it more interesting. Let's talk about this data enrichment. This is also what I think of as stateless. Is you get messages in on an input stream. You want to join it with some database or some service out there, and you want to kind of enrich the data, and you want to spit it out. Now, turns out this is a very rich and very important pattern. In offline processing, batch processing, typically people ETL all their data into a data lake. And now all the data is there. So if you want to join across many different data sets, it's very easy. And so you can derive a lot of value out of it. But in the nearline or the online world, this is actually hard. And we'll talk about why this is hard as we talk about scale as well. So remember this slide. In SAMZA, we came up with a concept called table. In this case, we use a remote table for accessing our Espresso database. And basically, the idea is, with this abstraction, you should be able to join your streams with your remote databases or services very easily. So we'll talk a little bit more about it as we deal with scale in the coming slides. All right, stateful processing. Aggregations are a good example. We also have stream joins, which I won't get into today. But if you take this aggregation example, you want to, in this particular example, we wanted to count the number of page views per member in LinkedIn and count it over a window of 5 minutes. So it's fairly easy to program this in the kind of high-level API that we have in SAMZA. By the way, if any of you use SAMZA from a few years ago, we didn't have this high-level API, and we had to manually stitch this together. So, as you can see, you want to kind of group by or basically partition by member ID. Then you want to apply a window, in this case, a 5-minute tumbling window. And then you want to do a count. Fairly easy to express this. Let's talk about what are the complexities here, right? So of course, windowing, there are different types of windowing, and you want your stream processor to be able to support all of them and in an easy way. There are also triggering mechanisms, so I won't go into the details for. But then, you need to think about what's the mechanism for windowing. You probably have heard about event time-based processing. There was a paper a few years ago, and there have been lots of talks and other blogs about it. Apache Beam is the kind of open source API from Google, which kind of concretizes the event time-based processing model. And the basic premise is that you want to process data based on the time when the data was created, not when it arrives at the stream processor. And that's mainly because there are delays in the pipeline. Maybe the device was offline, maybe there's a cross data center replication delay, or maybe you even replay your streams. And if you replay your streams, you want to make sure you bucket your events based on appropriate time. So Beam provides a nice API for this, and in Samza we have a Beam runner, which is used for by applications to kind of do event time based processing. All right, let's talk about some other things about that example that we just looked at. When we do a repartition based on member ID, in this example, there are two approaches to it. One is you can do like a classic RPC style repartitioning, and that's what is used by many frameworks out there. In Samza, we use a durable queue in between stages for doing these shuffle operations. And the advantage of that is that if there is any slowdown in a downstream operator, then it doesn't choke the whole system. This is also important when you do upgrades. It's important when there are failures. In essence, by putting a queue in between stages, it makes this whole thing a lot more reliable. Let's talk about other complexities. Accuracy is touted many times. In many situations, you don't really need exactly one's processing, but when you're doing some financial computations, you probably really care about accuracy, and there are, and then you're in this world. Now, it turns out the exactly one's processing kind of problem has multiple aspects, at least 3 aspects. I won't go into the details of each of these. I'm going to skim through it very fast because we need like a half-an-hour talk just on this. So the first aspect is ingestion, because there can be dupes in your ingestion. And if anyone says that, hey, your stream processor solves all of these problems and there are no issues with the ingestion, that's not true. There will always be dupes in your ingestions because there will be retries. The only way to deal with it is if your client can stamp a deterministic ID that you then use to dedupe it in your first stage of processing. So there's no way around it. The second aspect is dupes that are introduced during the processing pipeline. And there are multiple approaches over the course of years. The Chandy-Lamport technique is very kind of scalable. It's used by many frameworks. We actually have a design for this in Samza. Hopefully, we'll productize it soon. There are other approaches as well, like transactions and even dedupe again. But I would not recommend them. They're not as scalable as this approach, and also keeps the factoring right. The last part, which mostly people forget, is that you're going to put your results somewhere. And as long as you do idempotent writes, it's all good, no problem. And that's what most people do. But yeah, if you can't do idempotent writes, you can't update the same row again, then yeah, you have to do some kind of dedupe again in the database. And some databases support local transactions. Like in Espresso, yeah, we do have local transactions, so sometimes we end up using that. All right, that was a fast kind of overview of exactly events. Let's talk about scale. Now, when you talk about scale, there are actually 2 aspects. People want when they think about doing a stream processing app, many times their concern is, well, can your ingestion system handle this kind of scale, or whether your processing system can handle this kind of scale. So these 2 have to be dealt with separately. So when it comes to scaling ingestion, you're in 2 categories. One is you're running in the wonderful world of the cloud, and you're using the facilities available there. And if you're using any of the PaaS services like Event Hubs or Kinesis or PubSub, Google PubSub, then you don't have to worry about scaling them. The cloud provider takes care of it. But if you're running Kafka on-prem or in the cloud, then yeah, you have to buckle up, and you need to kind of know how you're going to scale your Kafka clusters. At LinkedIn, you've already seen the scale at which we operate, so we have to do a lot of work, and our teams kind of constantly improve the Kafka open source product. We have done a lot of work in the controller and lots of different parts. I won't be able to go into all of those details due to time constraints. Happy to talk about it after the talk. But the basic thing to think about is at some point your single cluster is going to be too big. At LinkedIn we run bare metal right now, and we don't want to go usually beyond 125, 150 nodes. That means that you need to have a multi-cluster strategy. So at some point, you want to be able to have a facility where your end users don't have to think about, hey, which cluster do I go create this queue, and okay, my other queue is over there, and so on and so forth. So we need like a way where end users just don't have to think about this kind of scale issues, and they create a topic and it just goes somewhere. That's something that we are currently kind of focused on. There are other lot of cost considerations. So scale is all great, and yeah, the product scale, so that's good, but you have to pay money for it. And there are a lot of optimizations. I just picked one of the big ones that we are doing this year. So till last year in Kafka, like if a broker died, if a disk died, then the broker basically became useless. And so we used to run Kafka with RAID on top of Kafka replication. And obviously that's not very efficient. So we did a bunch of work to make sure that a Kafka broker does not die if a disk dies. And now we're able to kind of run it the way it was designed for. And this kind of helps us save a bunch of costs, and also actually gives additional durability because of more replicas. But when we think about ingestion, the hardware costs are only one aspect. The bigger aspect is your cluster management itself. At our scale, disks die every day, machines die every day, and we keep expanding, shrinking clusters, and so as a result, there's always an operational problem. And to solve all that, we built this service called Kafka Cruise Control. It's open source in LinkedIn's GitHub. And it basically takes care of self-healing the Kafka cluster. If there are any failures, it detects it, makes sure there are no anomalies, and then tries to do the kind of rebalancing in a way that it doesn't saturate the NICs, saturate the brokers themselves, and impact live traffic. So there are a few big companies actually using it outside of LinkedIn. You might want to check it out. I won't go into the details of this. I just kind of left it here so that later when you look at the slides, if you're interested, you can kind of take a look. All right, that was about scaling ingestion. Now let's talk about scaling processing. When you talk about scaling processing, obviously you want horizontal scale. All that is great, but again, it comes back to costs. You don't want the stream processing to be like very expensive, so you need to figure out how you're going to optimize it. And then, of course, your scale is limited by your least scalable component, so you've got to know about what your bottleneck is going to be. Now, the typical bottlenecks, for the most part, our bottlenecks are usually around data access, I/O. The stream processors go really fast, but as soon as they touch some data, which is outside of the stream processor, then it all kind of slows down. So there's a bunch of optimizations that we'll talk about on how this can be kind of scalable. Now, sometimes CPU can also be a bottleneck. Usually, it's easy to solve that. You basically add more cores and add more containers. And we have some image classifiers running in SAMZA using TensorFlow, which are extremely CPU hungry. And obviously, for some of those cases, you eventually end up with better hardware like GPUs and such. So let's talk about the problems that we can solve around data access. So data access, there are two types of problems. There is the problem of accessing adjunct data, as we call it. This is the same example that we looked at earlier about doing a stream table join, basically to enrich your events that are coming in. Now, at scale, what this means is that you want to be able to do your database or service access using async paradigm. So you want to do async, you want to do batching, you want to do caching, and you want to make sure that you don't accidentally DOS your database or your service because other people might be using it. So when you add all that, it becomes pretty hard. for applications to kind of think about all this, so they are very worried about what they're going to break. So in the remote table abstraction that we've introduced in Samza, the point is to kind of take away this complexity, so that end users can kind of do these kind of joins with confidence. And some of these features are already kind of implemented in the upcoming release, and some of them hopefully will kind of do it in the future. But the way I see it, most stream processing systems will end up having to solve this problem. Now, turns out that at some scale, even regardless of what you do in terms of optimizations, if you're processing 1 million messages per second, and hitting a remote database is just probably going to kill it. So for these cases, what we do is we basically internalize the remote database into the processing tier by creating a durable cache. We use Brooklyn, which is our change capture product, to do that. And we repartition the data, and now all the lookups are local. So this is great because with this there are no issues of DOSing your remote database. Now the problem is, historically this was pretty hard to wire up, and that's why, again, the point is we wanted to make it accessible, so the complexity is kind of taken away. So now with the table abstraction, again, now we're able to kind of terminate this change capture stream into a table, and then you should be able to join with that table so that all your lookups are local. All right, that was all about accessing adjunct data and data enrichment. The other aspect is, if you're doing stateful processing, then you need to maintain your state, right? Now, of course, you can maintain your state. Again, let's say you're doing a count. You can maintain your count in a database, like any standard database out there. And that'll work. But at some scale, again, you want to be able to kind of do all of these counts and in all of this state management in a very efficient way. So in Samza, we have this, by default, if you're doing any kind of stateful operations, we use RocksDB, which is an open source database from Facebook. And we also kind of have a notion of a changelog to kind of copy the data over to a durable Kafka topic. And that way, if a machine dies, we can replay it. And yeah, performance obviously good with this. Now, when we're talking about stateful applications and maintaining temporary state, one call that I wanted to make was, it only works if you're doing incremental checkpoints. Like at LinkedIn, some of our applications have terabytes of state. Even if you have gigabytes or a few hundred megabytes of state, if every time you checkpoint, if you're going to save all of the data, like a full snapshot, then it's just not going to scale. So this is an area, like Samza has always only supported incremental checkpoints, but this is an area where most of the other stream processors have also added support, and over time I would imagine this would be the predominant way of doing checkpointing. Now we talked about local state, just some numbers. Yeah, so local state can be about 100x up to 100x faster than accessing a remote DB, and obviously latency is also much better. So all this is good. Yeah, but there are, you don't hear a lot of people using local state, and that's mainly because the system needs to make it reliable. So in Samza, we've done a lot of work over the years to make sure that local state is reliable. That is, when you're doing upgrade or if a machine dies, you want to make sure that your least amount of state moves around, right? So it's like a database. Your processor basically has an embedded database. So you have to do a bunch of work, and Samza basically integrates with Yarn when we're running it as a service, so that the state is what we call host affinity is not broken, so that the containers go back to the same place where they were running and start reusing the same state that they were using before. Some of the other stream processors are also adding support for this, and it's pretty critical if you want to use local state. All right, let's talk about other things. Sources. So we already talked about sources, like there are a lot of sources out there. The main thing is that your stream processor should have support for pluggability of sources, and that's all good. But there's one source which kind of sticks out there, and that's HDFS. And the point being that many times you want to take your streaming app and you want to run it as a offline batch app, and maybe you want to do some experimentation. Maybe you have a new ML model that you want to try out with some 1 day worth of data, see the results, and see if it's good before you push it out to your streaming environment. So yeah, so there are a lot of these cases, excuse me, where you want your stream processor to run as a batch application. And for that, basically in SAMSA, the idea is all you do is change your input to HDFS, and the rest of it just works. And that kind of sounds weird, but yeah, it does just work. The idea is that SAMSA still operates like any streaming application, but basically the stream ends. So there's a notion of an end of stream, and when the stream ends, the app terminates. The rest of it, like as long as you're doing event time-based processing, you're bucketing appropriately, the results are going to be exactly the same. The other cool thing here is that all the stages of processing are going on in parallel, so it's actually more efficient. All right. So the next one is language. Language is very important. And yeah, everyone has Java APIs, and when you think about stream processing, it's usually Java. But SQL is probably going to be the thing that's going to, the way I see it, transform stream processing, make it very ubiquitous. Very similar to what HIVE and Pig did for MapReduce. Without HIVE and Pig, it was really not very accessible. So same thing with SQL. So in SAMSA we support Apache Calcite SQL. So we don't have our own flavor of SQL. It's basically what's used with Apache Calcite. And the idea is that with this you can do all of these kind of interesting data enrichment applications and so on and so forth very trivially. You can even, like, for example, let's say there's a database, in our case Espresso, and you want to kind of get the changes from that and create like a secondary index or a secondary database, update a Couchbase cache or whatever it is. You can just express it in SQL very easily, right? And that just takes the whole complexity out of the equation. You can also do stateful processing, and it's pretty much the same. You can express your windows and so on and so forth. So yeah, so basically just completely kind of makes the playing field level. Now at LinkedIn, we also had a bunch of old Hive and Pig scripts which were being used for our daily dashboards, hourly dashboards, and such. And we had this need that we wanted to do real-time kind of reporting. And for that, one of our teams basically converted the Hive and Pig kind of scripts into Calcite, Apache Calcite's intermediate representation, and from that we can kind of execute it as a SAMSA nearline app. So that pattern is also pretty exciting, and now we are actually evaluating if we can do this for other kind of DSLs as well, like including Spark SQL as well. We already talked about Apache Beam, and Beam does support pluggable engines. But what's very exciting for us for Beam is that we can get the support for Python. Python's a big deal for our ML engineers, our tools engineers, and with this, the hope is you can run Python-based stream processing apps in SAMSA. And hopefully, as Beam adds more languages, we'll look forward to supporting more as well. All right. The next one is that, yeah, you want to run your apps anywhere in any environment. And that means you might be running in the cloud, you might be running on-prem. And that means that we want stream processing to be offered both as a library that you can run anywhere, or you want to have a stream processing service where you can deploy your apps. And that's what our goal has been at LinkedIn. We offer stream processing as a service, which means that our application developers basically submit their stream processing apps in Java or in SQL, and we deploy it into a Yarn cluster. We manage the capacity for the Yarn cluster and leverage all the goodies that Yarn provides us. For stateful applications, we make sure we use Yarn in an appropriate way that state doesn't move, and we get host affinity. For Samza SQL, this is a big deal. The whole point of writing something in SQL is that you shouldn't have to worry about figuring out what's the container count, what's the memory, and every other thing that you have to kind of think about for tuning applications. In SQL, the goal is that all of that should be automatic. Now, this also should be the same for any Java app. So as far as stream processing is concerned, auto-tuning is still like one of the areas where I've not seen any stream processor being really good. And hopefully in SAMS also our focus is to kind of make this really kind of seamless. Today people spend like sometimes weeks or a month to figure out what's the right settings in terms of scale, cores, memory, and so on and so forth. And that needs to go away. And yeah, you want to run your app anywhere, which means you want to use it as a library. And when you use it as a library in Samza, we use ZK, Zookeeper for coordination. But the rest of it pretty much is the same. You launch it, you run it, and yeah, and cool. So let's see, how are we doing on time? Actually, there is no time here. Okay, good. Yeah, we are pretty much to the end of it. Looks like I went too fast. The last one is, yeah, you need really good tools. And this is an area where I think the stream processing ecosystem really suffers. If you see the kind of tools that you have in a lot of the offline systems, it's really, really good, right? And this area is now improving. You want tools for your schema management. Obviously, schema evolution is a big deal. Managing ACLs, topics, managing your job itself. For every streaming job, you want a dashboard where you can see if the job is lagging behind or is it caught up. You also want to monitor your ingestion systems. So yeah, great tools are kind of minbar. And we have a bunch of tools that are open source for this, like Kafka monitors our Kafka clusters. It basically sends these synthetic events through every topic, not every topic, through a set of topics to make sure the Kafka systems are monitored. Burrow is another open source tool that is used to see if the application is making progress. Yeah, we need a lot more tools. All right, so with that, that's kind of the end of the kind of core presentation on what I think is the ideal world. This is just a list of open source projects. Check out the upcoming release for Samza, which is Samza 1.0, where some of the things that we talked about will be available, and we'll have much improved documentation, which I think we have suffered in the past. And yeah, you can check out the Kafka tools as well that we have listed out there. With that, thank you. And yeah, we are hiring in case.